we can't really compute this. If it was a normal base, say 3, we could do 3 squared or 3 cubed, even figure it out in our head maybe. But with a number like this, what you really need to do is use your calculator. So if you get your calculator out sometime, what you're looking for is a little key that looks like e to the x. And that's what you would use. For example, if you put in, we know a number raised to 1 is just that number. So if you put the number 1 in your calculator, then you hit the e to the x key, then it's going to spit out something like this. It'll stop at some point. So that's how it would work. So for example, if I had wanted to evaluate this natural exponential function for say 1/2. Well, what I would have to do then is key in 1/2, so I would probably put it in as 0.5, hit the e to the x key, and then you're going to get some result. It's going to be less than 2.7 because smaller exponents give you a smaller result. But anyways, try it out. I'm not sure what it equals. But that's what the e to the x key is for, and that's really the only way to calculate these. Okay. This is going to pop up in the next section a lot when we look at logarithms. We'll look at natural logarithms, and e pops up again, and we'll be seeing it on and off probably throughout the rest of the book. Okay, there's an important rule now that's going to help us to solve problems, and that is the exponential uniqueness property. Unique. And basically it's trying to talk about the uniqueness of exponents. So for example, it's kind of stated like this. So basically what it's saying, first notice the base has to be the same. So if I have a base raised to a power and it's equal to that same base raised to a different power, they have to be the same power. Okay, and likewise, if they're not equal, then these can't be equal. So it works both ways. So it looks like a pretty straightforward, simple rule, but let's see how we can use it. So let's start with this. See, up to this point, we're used to solving problems where x is just in the main flow. Now we got a variable up in the exponent. How are we going to solve that? We haven't really done much of that yet. This rule will help us. Right now we got a problem. These bases don't match. But if I could make them match, we could use this rule. Well, these both look like they're based on powers of 2, so let's try that. So if I look at 32, I could even figure it out on my fingers. 2, 4, 8, 16, 32. That's 2 to the 5th. And 16, I went past it when I was counting that. 16 is 2 to the 4th. So what I can do is substitute this in place of 32. So instead of 32, I write 2 to the 5th, raising it to the x power. Over here, instead of 16, I'm going to put in 2 to the 4th, and I'm going to raise that to the x plus 1 power. Okay. Now back to our rules from last time. When I raise a power by another power, I multiply the powers. So 2 to the 5x. Over here we have 2 to the 4x plus 4. So I multiply 4 times all of this. Okay, now that I have the same base, that means these have to equal. So set them equal and solve for x. Subtract 4x from both sides, and x equals 4. All right, I've got one more example of using this. It's a little bit different. This one involves e, and the thing here is, you'll see it as I write it out. The thing here is, we already have all the bases matching. That's good, but the problem is, I can only have it real simple. It's got to be base to exponent equals base to exponent. I got too much stuff here. So what I need to do is start working with our exponent rules, using the distributive rule here, trying to get all this expanded out, and then get it down to just one e on each side of the equal sign. So that's our goal. So here, I'm multiplying like bases. When you multiply like bases, you add the exponents. So here I'm going to have e to the x plus x, that's 2x. And here I'm going to have x plus, there's a 1 there, so when I add those exponents, I get this. All right. Over here, I just want to get rid of the denominator. How do you do that? Well, just move it up, but when I move it up, what happens to this sign? It's going to become a plus. So let me go over here and work this. Here's the numerator here. That entire numerator is going to be multiplied by e to the x because I'm bringing this up and it's going to change sign. So multiply these, you add the exponents. Multiply these, you add the exponents. But that's 3x plus 1x, that's 4x. Okay, now if I look, I can subtract e to the 2x from both sides. Now we got what we want. I have one base to a power equals that same base to a power. The powers or exponents have to be equal. So x plus 1 equals 4x. Subtract x from both sides. Divide both sides by 3. So that's how we can use the exponential uniqueness property. And we're going to use it again in a minute. I'm going to go now to a word problem and see how this all works out. Okay, let me get this centered here. Okay, some background, and this was actually a problem taken out of the homework, and they provide the equation and talk about it, but let me go through it here. This is just a half-life equation. So Q of t is, that's basically a function evaluated at t, so that's the amount of stuff you have at time t. So when t is 0, you got everything. As t moves on, this is a half-life problem. You're starting to lose material every so often. So amount of material at time t. Q0, the way you read that is Q naught, and that's a standard symbol here. What that means is initial or starting amount. So you'll see that little naught symbol used a lot. So Q naught is just, what was my starting amount or initial amount? T is the time that's elapsed, so how much time has gone by. And then H is your half-life time. So some things here to watch out for. This is going to change as time changes. Time changes because it changes as it goes, right? Initial amount's not going to change. Whatever you start with, you start with. Half-life time is not going to change. The half-life is the half-life of the element. And then the only other thing to be careful of is these right here. These are both times. They have to be the same unit. So they either got to be hours, minutes. You can't mix them. Okay, so keep that in mind. So here's our specifics. We have a sodium isotope, has a half-life of 16 hours. So right now, before I get into the actual problems, I know that at some point in time I'll have some of this stuff. I'm going to start with a certain amount, and I'm going to run for a certain amount of time, and my half-life is 16. So that formula is good for this particular isotope no matter what we ask down here. All right, so what are we asking first? How many grams are left? So we're trying to solve for that after 2 days. So time is days, 2 days have gone by. Unfortunately, the half-life is in hours, so I need to convert this to hours. So 2 days times 24 hours per day equals 48. So 48 is going to be T. All right, so here's our formula. We're solving for this guy. How much did I start with? Well, we don't know because I forgot to write it. We're going to start with 128 grams, let's say. So that's our sample. Okay, now we have a complete problem. Sorry about that. So if I start with 128 gram sample, Q naught is going to be 128. And again, that was our starting point, so that's going to be the same no matter what we do. So we have 128 grams starting, 1/2. We found out T was 48 hours over 16 hours. Now we just solved this for Q of T. And here I should put in 48 because we're evaluating at 48. So Q of 48, so what happens, what do we have left in 48 hours? 128 times 1/2, reduces fraction, it becomes 3. Use our exponent rules. Everything in here gets cubed, so 1 to the third is 1, 2 to the third is 8. And then if I divide 8 into 128, I'm going to get, goes in once, let's see, 48 should be 16, and we're talking grams here. So 48 hours, 16 grams remain. Okay. Let's look at the second one. The second one, we're kind of doing the opposite. We know what we want to have left, but we don't know what the time is. So again, here's our equation. 1 gram remains. That's my amount after time t. So I want a 1 here. 128. Our starting point was still 128. Here's the formula. I don't know what T is, but the half-life never changes. Okay, so we're looking like this. All right, so this looks weird. But what I'm thinking is we have a base and an exponent. Maybe I could get a base over here based on 2. So to start with that, let's get the base by itself. Let's divide both sides by 128. Now, if I could get a 2 here to some power, that would be great. Well, if you start looking at 128, and you could even count it out on your fingers if you need to, It's actually 2 to the 7th. So if I replaced 128 with 2 to the 7th, we're almost there. I need just a 2 here, but that's not a problem. If I rewrite it like this, that's still 2 to the 7th down there, so that's what we want. So now we can use that rule of the uniqueness rule. So I got the same base, it's 1/2. That means these have to be equal, so set them equal. Multiply both sides by 16. 7 times 16 is 112. And that was hours. So that's how you can use it in some problems. And we're going to move on to section 5.3 next. And that's going to be logarithms. You can look ahead if you want. There's a lot in there I'll have to cover. But logarithms are actually going to be the inverse of exponential functions.